Welcome back once again. So, in the last class we introduced the Schwartz space. The idea is to develop Fourier transform and convolution for the distributions, and we also motivated, we introduced Palevina theorem, and which proves that you can't develop Fourier transform for every distribution. So, we introduced the class of functions which are rapidly decreasing, and Schwartz space is nothing but the set of all functions and all its derivatives are rapidly decreasing C infinity function. And then we also seen an equivalent criteria that a function is in Schwartz space, then you have an equivalent criteria, and especially the third one, this one, it's enough to check that for a C infinity function for all k, and this is for useful for the computations. So, with that now we can define a topology also. You have to know topology all the time. Topology on zeta. When topology on zeta is, we say phi converges to 0 in zeta if and only if, of course, if and only if P L F L P L phi L converges to 0 uniformly in Rn. Okay, that is uniformly in Rn. This happens for all polynomials P and all operators, linear differential operators L with constant coefficients. So, we may not with the constant. So, for the time being we consider P is always polynomial, L is linear operator with the constant coefficients. With this you get the inclusion D contained in zeta and contained in E. E is nothing but your C infinity. So, you have D contained in zeta and contained in E. So, you can define dual spaces D prime, you can also E prime, and you can also define zeta prime. Okay. So, E prime is already identified with distributions with compact support, that means any distribution can be extended to E. Now, on zeta prime you can define on zeta prime a topology can be given. Topology can be given, that is not a difficult thing, that Tn in zeta prime converges to T in zeta if with Tn of phi converges to T phi as I do a Weikstradt topology for all phi in zeta. So, that is a top. With that inclusions you have this inclusion. So, you see, and this is the distributions with compact support, and this is distribution, this is the distributions with the compact support, and this one distributions, these are called tempered distributions. This is all distributions, Okay. That means when a distribution T in D prime, if we can extend T, to zeta, that means again we denote the extension by saying as a continuous extension Ct to R, then T is a tempered distribution. That is the way you will see. Only those distributions which can be extended to zeta are called tempered distributions. Okay. So, tempered distributions basically means if T phi can be defined for all phi in zeta. Okay. So, that distributions with the compact support can also is because if the distribution is a compact support, it is already extended to E. In particular, there is an extension of zeta. So, every distribution with compact support, distribution with compact support are tempered distributions, are tempered. You see, you already have this all distribution. That is trivial because you have already have an extension. So, with that we will move on to something. So, now Fourier transform is an, you see, Fourier transform you already seen the zeta to zeta, and also Fourier transform is one which is extended to L2 to L2. This is another way of extending also. So, you can directly do Fourier transform and then zeta is dense in L2. Since because d omega is dense in L2, which we probably will see again during the convolution time. So, which is an L2 isometry. So, the f is the way you have developed already is that you have seen the Fourier transform from L1 intersection L2. Okay. You can do the same analysis with the whatever done for L1 L2, you can do it here, and then you can see that Fourier transform if f is in zeta, you can see the Fourier transform is also in zeta. So, which can also be because you already done that essentially you have done everything, computational derivatives and all that. So, when you have a function f in zeta, because zeta is always in L1, you see. Yeah, that probably I will give you an example soon. I will give. In fact, you are going to see that it is in LP. Okay. So, that for the natural Fourier transform is defined. So, but if f is in zeta, you will actually get a f hat is also in zeta. So, you have the Fourier transform maps zeta to zeta. Okay, and you can derive exactly the procedures you have done in L1 L2 intersection L2 all can be proved for zeta, and then you can see that all the formulas and isometry everything. So, you have a space where it preserves the Fourier transform is preserved. So, let us have some simple example. The function e power minus mod x square, this does not have a compact support and hence this is not in D, but e power minus mod x square is in zeta because it is rapidly decaying. Is decaying all its derivative always you have exponential. So, the decay is more than the polynomial. So, even if you multiply by polynomials, that is what you precisely want for rapid decay, and it will taken care of by the mod x square. But e power mod x square, this is not decaying. So, this is not in zeta, but e power x square is a smooth function. So, this is in E, that is C infinity of omega. You can also prove many things, that is one example. So, if f and g is in zeta, so you can prove a lot of things that implies f g is in zeta. So, there are a lot of properties about zeta. It is an algebra PLF is in theta, PLF and LF and PF, LPF, these are all. So, it is a the zeta is preserved under all these operations in that way. And one interesting result which probably maybe the technique is useful, probably you have seen it anyway, but let me for the sake of completeness prove it in case I think probably it is proved, but it is another thing. Zeta of Rn is contained in L1, is embedded in L1. In fact, zeta of Rn is in LP, okay, for 1 less than or equal to P less than or equal to infinity. So, let me give you a quick proof of it. As I said, the proof trick you want to do it, the same trick can be employed there. So, assume f is in theta, let f is in theta. You want to show that compute integral of mod f. So, I will this kind of thing. So, I will write down 1 by plus mod x square o power minus k. I will choose my k later, but this is true for any k, mod x square power k f is there for any k, for any positive integer k or negative integer. So, this is f is in theta, this is a bounded quantity. So, I can tell this one less than or equal to supremum of modulus of. So, this is what the usage of that equivalent formulation k f, because this is bounded since f is in theta. So, this one, this is finite and this you will get it integral of 1 plus mod x square power minus k, you see. But this quantity is finite if k is greater than n by 2. So, you can choose some k greater than n by 2, because this portion is finite for any k because of f is in zeta. So, the similar trick can be used to prove, yeah, okay. So, and the continuity can also, this is a problem. Okay. Hello. Okay. The continuity can also be proved easily if FL converges to 0, that is where the continuity in theta, because that is a uniform convergence of all its derivative. You can use this same trick here, we have written here. So, I will leave it as an exercise for you to prove it. Okay. So, you can use this again and then you will get this convergence, the boundedness here. Using that boundedness, because Fn converges to 0 uniformly, you can actually show that Fl converges to 0 in L1. Okay. So, the complete the proof by filling up the gaps, that is what the exercise, and then prove this result for even for LP. So, to apply LP, that is all. So, this proving this convergence is the same estimates will get you the proof of that convergence. Okay. So, now, so we have already told you if f is in zeta, you will get f hat is in zeta the same way you have proved, because you can show that if f is rapidly decreasing and all its derivatives are rapidly decreasing, you can show that the Fourier transform is also rapidly decreasing and all its derivatives. And no f hat at L2, you get it. I told you there will be a constant sitting according to your formula. Okay. Alright. So, what are we proved? So, zeta is in LP. You can also prove that because it is true for every LP. By taking duality you get every LQ. So, equivalent to saying that LP contained in zeta prime. So, you see all LP primes, all LP functions. So, this follows because zeta is in LP for all p 1 less than or equal to p less than or equal to infinity. So, taking duality LP dual will be some LQ. So, you will get all LQs are in zeta prime, but I am using the same thing here. Okay. So, you have this function. So, you have all these embeddings zeta contained in LP that contained in zeta prime. So, all LP functions. So, now you see you can define once you define, we are going to define Fourier transform of zeta prime, the elements of tempered distributions, that way you get your all prime. So, for every polynomial defines a tempered distribution, polynomials P defines a tempered distribution, tempered polynomials tempered distribution in the following way: P acting at phi is equal to integral of p of x dx, and the right hand side is finite because phi is very rapidly decreasing for all phi in zeta. Of course, these polynomials will not define distributions with compact support. It will not be in E prime, okay, because it does not have any compact support. So, you do not get that one. Okay. So, let me give you one more definition, something like a dual property of rapidly decreasing. Okay. What is called a slowly increasing at infinity, slowly increasing at infinity. Okay. F is slowly increasing at infinity, if there is a k positive, such that 1 plus mod x square whole power minus k by 2 f is bounded in R. This is equal to say that f can't grow more than a polynomial. That is what it really is. Equivalently, this is equivalent to there exists a polynomial p, there exists a polynomial p such that modulus of fx less than or equal to mod px. You see. So, it can be estimated by a poly, it can't grow more than. So, it is a exponential are generally called, it is like an exponential decay, exponential goes to infinity faster like e power x, etc. Polynomial is always something like a normal growth, like an integral growth, it we call it. So, the simple proposition is immediately any slowly increasing function, because it is slower than polynomial and polynomials are tempered distribution, any slowly increasing f is tempered, because that is trivial, because already we defined that polynomials define is less than the polynomial. So, tempered. So, you have now all slowly increasing function. In fact, any derivative of slowly increasing function, any derivative of slowly increasing function f defines a tempered distribution as defines a tempered distribution as. So, you will have that distribution given by, please keep it in mind that d power alpha, even though f is slowly increasing function, the derivative need not be a function. So, when I am writing t d power alpha of f, do not mistakenly taken that this is a distribution given by a function. No, it is given by a distribution only. D power alpha can be a function, not be a function. So, just because it is writing t d power alpha of e, that is my definition of the thing, defines a distribution. So, this call it a distribution given by minus 1 power mod alpha into integral of f d power. You can verify that immediately, it is a distribution, it is a tempered, and this is defined for all phi in zeta. So, when I say that, you have to have the meaning not just for phi in d, you have to have the meaning for all phi in zeta. The interesting case which I do not want to discuss, may not prove it here, I am not going to prove it here, the converse is also true. That is why the name is tempered. A converse is also true, in the sense that if t is tempered, so it is related to the polynomial basically, you see all their functions and its derivatives. Okay. Tempered, then there exists a slowly increasing function, essentially it is of polynomial or its derivative type, that is what it says that, but the function need not be a polynomial, it is controlled by polynomials. Slowly increasing f and then multi index alpha such that t is equal to, t is given by this way, where this definition is this one. Okay. So, t that one, and that is a reason is a basically called the definition. It is also worthwhile to recall this duality property. You see, the Schwartz space is essentially the set of all functions which is slowly decreasing, rapidly decaying. You see the duality coming, rapidly decaying, and all its derivatives are rapidly decaying, but here you have a slowly increasing and its derivatives. So, that is a dual space. So, you are basically characterizing the dual space in that spirit. Okay. So, with this we will go to the definition now. Okay. Fourier transform of tempered distributions t given by in zeta prime. Okay. So, definition is already know that if t is in define t hat of from zeta to, again is from zeta to r by t hat of phi is equal to t phi hat. The definition is well defined, because if phi is in zeta is well defined, as since phi is in zeta implies phi hat is in zeta, and phi n converges to 0 in zeta. These are all property of the Schwartz space, implies phi n hat goes to 0. Let me write m. Phi m hat goes to 0 in zeta. That implies if phi m goes to 0 in zeta, then t hat of phi m goes to 0. That is, t hat is also in zeta prime. So, the Fourier transform is defined as a member of zeta prime. So, the Fourier transform is also a. So, the Fourier transform is a mapping, in fact is a bijection. You already know that Fourier transform is an isomorphism. F is from zeta to zeta is an isomorphism, and F from zeta prime to zeta prime is a bijection. You have all these property more or less free once you understand the Fourier transform in zeta to zeta. So, maybe one more comment. What other things you want to prove it? Few more things. There are a couple of more things so that it will be over. I can start convolutions probably 26. I have done something before that also. So, maybe I will stop here and then I will continue. Okay.